So for this demonstration, we're going to be exploring the concept of surface tension of water, and to do that, we're going to compare how many drops of water we can get on the head of a single penny. So I have here a dropper with just tap water, and I'm going to count how many drops I can get on the head of this penny. 1, 2, that's 10. It's important to notice how the water is collecting basically into a corner. It is bunching itself up. See, even as I'm trying to put it on the edge here, it is packing in on itself. I'll let it set for a second. So you can see it's basically rising upwards a little bit. I'm trying to be very careful here. Oh, look at that. It's kind of like just over the lip of the penny, but it's still staying there. That's because the surface tension, the polarity of the water molecules are holding it together, even though there's gravity pulling that water down. I think I can get maybe 1 or 2 more. My record is 30. Let's see if I can go for 31. 29. Oh my God. Boo! I got too excited. And so it goes. All right, so 29 was the total number of drops that I could get on the tail side of this penny. Now we're going to compare this to the alcohol, ethyl alcohol that I have in this other dropper, and we'll see how many drops of ethyl alcohol I can get. 1, oops, see how it's already coming out. 2, 3, and if you can notice, 4. It's spreading out. It's already spread out over the entire head of the penny pretty much, whereas with 5, the water drops were still bunched into one corner. 6. It's interesting to see how the water has now spread out as the total surface tension has decreased, as it has more room to expand. 7. 15. You can even see the drop of alcohol is coming out faster as it's trying to get out of the dropper. 16, 17, 18. Okay. So this value might vary according to how good you are at dropping the liquid or how fast you do it. There's going to be other variables, but all things equal, we can see that because of the properties of the water, that more drops will be able to maintain themselves on the surface of the penny for water compared to alcohol. So as I was saying, your miles may vary, but when we looked at it in my lab, we had 5 students, and so we got one student got 23 drops, another one got 25, another one also got 25, one person got 22, I think that was me, and then another student got 30. So we had an average of 25 drops for the water. For the alcohol, the numbers were 20, 28, 14, 22, and 21 for an average of 21 drops. So the difference between 25 and 21 is statistically significant. That does seem to suggest that there's going to be a difference in the properties of the water versus the properties of the alcohol that would affect the number of drops that can fit onto the surface of the penny. Now, what's wonderful about this lab is that it offers lots of opportunities for asking questions to follow up. For example, in the demonstration that I did, you saw that I had both sides of the penny on the tail side. One student asked the question, well, what about heads versus tails? Would the total number of drops differ? Would one be able to hold more drops? Honestly, I have no clue. That sounds like an awesome follow-up experiment. Another student asked, well, how about the height of the dropper? We didn't actually attempt to standardize the height of the drops. Some students held them closer to the penny than others, so that might affect it. What about the material? What about an identical penny? I use older pennies, but what about newer pennies? Maybe the differences in the material of how modern pennies are compared to pennies made in the 20th century. Maybe there's a difference. I don't know. These are wonderful things to experiment with. And what's really great about this is you don't really need a whole lot of equipment. The chemistry does not need to be flashy or explosive or anything like that. It's just a matter of asking some follow-up questions and then being willing to try it again and pushing or publishing your results. That is basic science. Good times.